Right now, we have a great talk. Rohan McLure, going out on a limb, accelerating elliptic curve cryptography. Let's welcome him to the stage.
Hey. Thanks for coming to see me present basically a maths lecture from a terminal. Hi, my name is Rohan. I work for IBM. I do software support for the Power architecture. I predominantly work on Linux kernel stuff, so Arch PowerPC. The Power architecture is the instruction set which our modern server class processors run on. As an aside, I also work on cryptography libraries, so the general Linux on Power software ecosystem, the largest of which is OpenSSL. This is a library which probably doesn't need an introduction at a BSides. It's a cross-platform cryptography library, and in fact, the most widely used one. Serves as an upstream for some of its forks, and it's heavily geared towards performance, written in some pretty low-level C, as well as architecture-specific optimizations in assembly. The assembly is written in Perl as well, which is a lovely caveat. Anyway, my work is to do with elliptic curve crypto. So I took this one particular algorithm and, in fact, completely reworked its implementation. So that's 2,000 lines of C I managed to ship into OpenSSL. And we're seeing some pretty strong speed up across the board with it, as well as a fair candidate for ASM optimizations by your relevant architecture. Why this curve is relevant is because the NSA has put forward their advice on the suggested curves for every different commercial purpose. And so for digital signature generation and verification, as well as key exchange, this is the recommended one. Sort of its key size fits within the kind of Goldilocks, I suppose. But funnily enough, it's actually the last such curve in OpenSSL from NIST to receive sweeping optimizations. So yeah, against an already optimized for power baseline, which I've written as Montgomery, we're seeing about 4.5 times speed up, which is, yeah, more than I basically could have possibly expected. So yeah, there are already assembly optimizations into that number. So if you remove those, that brings us up to about like a 5.2x speed up off baseline. And then in verification, we're seeing a 1.7x speed up. So these are substantial. This talk is about where do they come from, basically. How do you make crypto that much faster? A little bit of background on elliptic curve crypto. So it's a public key cryptography scheme. Equivalently, you may have heard of asymmetric cryptography. And it's largely supplanted in the process of supplanting RSA. So for a smaller key size, you actually get a comparable degree of security, which is nice. And so, the upshot I'm going to give is just allows for better performance, really. So what is an elliptic curve? This will appeal to the mathematicians in the room, although I'm not going to go into too much detail. Essentially, an elliptic curve is the set of solutions to the following equation in polynomials equipped with an algebraic group. And so you use some corollaries of Bazou's theorem, and you get a notion of what it means to add points together on the elliptic curve, to subtract points, as well as a notion of identity through points at infinity. For performance, however, it matters only not what operations are going on and how you get a discrete logarithm problem. It matters what the underlying mathematical objects are. And so, or at least at that level is where I've put my optimizations. So you need only know what x and y are, basically. Well, they're elements of some sort of finite field. There are two types of finite field. There are not very many types of finite field at all, but there are two types which matter to us kind of in the cryptosphere from what I'm aware. There's binary fields, which we won't be talking about, and basically just integer arithmetic modulo big old prime. One real advantage of ECC is that these big old primes don't change, unlike in RSA, where your modulus is determined by key setup. Programmers in the room will be familiar with the percentage operator in most languages, but we need our modular reduction and all of our arithmetic to be constant time because it's crypto. A bit of a primer on modular arithmetic. Essentially, you can think of the modulo operator as divide by our n and take its remainder. But modular arithmetic, basically, it's a ring homomorphism. I shouldn't have said basically. But that triple equals operator you're seeing, that means that the left-hand side and the right-hand side share the same remainder. And so you can have that triple equals operator in as much as you're only ever adding or subtracting multiples of the modulus. And then the lovely thing here is that when you do arithmetic, additions or multiplications, you can reduce your numbers modulo n at any stage, or partially reduce them, etc. And when n is a prime, you get a finite field. Delightful. Now, zooming back a bit, just in fixed point arithmetic, there are some performance pitfalls. So suppose you have some a and b bounded above by some n. Then the upper bound of their summation is going to increase arithmetically. That is, 2 operands added together, less than 2n. But their upper bound via a product is going to increase geometrically. So 3 terms is bounded above by n cubed, 4 terms by n to the power 4. And so we're going to need double the number of bits in order to store their product. A bit of a solution here is to use some sort of data structure which is permissive of variable width integers. And you can build that up using what's called a lim representation. So the idea is you have your LIs, which are themselves fixed width integers, and you concatenate these fixed width integers together, just like you might digits of a base 10 number. So 2 to the power n, in this case 64, is our radix. And we're concatenating our limbs together. Every bit in lim 1 is less significant than any bit in lim 2, etc. Well, one strength of our algorithm is that we don't have to do carries. We can leave carries basically to the last possible moment. We can lazily carry. And so one function we'll want to write is a multiply or a square kernel, where we're going to want to add together these cross terms, these AIs times AJs. Each of the AIs, let's say, is bounded above by 2 to the 64. We run into an obvious problem. We need some sort of larger backing type. We need to do that cast to 128 in order to store the result. What we've just done is we've done redundant limbs. That is, we allow for each of the LIs to actually be larger than their distinctor, their radix, the difference in place value between limbs. All right, well, we've done that, and it's still equal to 64. And so we end up with the cross terms fitting neatly inside of an unsized 128-bit number, but we don't have any space to actually add the cross terms. OK, well, we need to introduce more redundancy, and I like to call these unsaturated redundant limbs. The idea here is that we set a precondition on our arithmetic, which is that the limbs which compose A are going to be no larger than 2 to the 56. What that exponent is, in our case, our limb width is 56. It doesn't really matter, in as much as we can promise that we'll never overflow in our calculations. And so now, when the limbs of A are suitably small, we can't possibly overflow in our 128-bit type. This is a little bit of a Unicode diagram of what unsaturated redundant limbs can look like. So limb width, that is the difference in the starting point of each successive limb is 56 bits, but the underlying type can be 64 bits. And so to the left of those dotted lines, you can have a little bit of overflow. You can have a little bit of high bits, which redundantly store the contents of higher limbs. So basically where two limbs overlap vertically, we're going to have to do some sort of addition to remove the redundancy. This brings us finally to the overall implementation I wish to use, called Salinas. The basic premise is that we're going to keep writing these kernels until we've comprehensively produced our algorithm, which are going to be able to compose. So the inputs and outputs to this function should be reduced modulo our prime, and each of the limbs should be minimal. We can then do some operation like a square or like an addition, something which could possibly overflow and pad out into these 128-bit limbs, these larger 128-bit limbs. And so long as we reduce, and so long as we're able to reduce the final state of temp, then we can now arbitrarily compose these square reduce kernels or something similar. A little bit of a primer to understand the rest of this talk. So we know what a polynomial is. A polynomial is just a weighted sum of powers of some variable, let's say t. And you'll observe that in summation form, this looks very similar to the value represented by a multi-limb representation. We've just swapped out our radix, that is 2 to the n, for t. And so we can actually think of arithmetic modulo a Salinas prime, that is a prime easily expressible as some low-order polynomial of powers of 2. We can re-express our problem in terms of reduction in polynomial rings, basically. And so a smaller prime prescribed by NIST is P224. And so if we let f of t be this degree 7 polynomial, then our prime itself is just our polynomial evaluated at 2 to the 32. And because we're doing arithmetic now mod f of t, we can manipulate these polynomial expressions. The upshot here is that whenever we get a lim 7, a lim 8, or anything higher than that, we can actually re-express that lim in terms of lower limbs. So t to the 7 has the same remainder mod f of t as t cubed minus 1. And so basically, the substitution, the summation from a couple slides ago is saying that lim representation is just polynomial coefficients. A lim is a polynomial coefficient, where t is 2 to the power our lim width. And so our inputs to a multiplication, a and b, are just polynomials. We polynomial long multiply them. Each of them was in terms of 1 through t6, and now their product is in terms of 1 through t12. And so we take the kind of reduction rule from earlier. T to the 7 can be expressible in terms of smaller powers, and we do the same up till t12. And we can now reduce all the high limbs using some slick maths. The problem is that we're actually dealing with a harder prime. This is likely why there's been no Salinas implementation so far in OpenSSL prior to this patch. And all of the indices, they're neatly divisible by 32, but we would really rather not be wasting, if we're on a 64-bit machine, we'd really rather not be wasting half of our registers with empty arithmetic. And so let's actually pick our lim width to be 1 byte less than, this is arbitrary, 1 byte less than the maximum size, so 56. This is an optimization for if your architecture provides fast instructions for byte addressable quantities. And so we end up with this absolutely horrendous looking polynomial in terms of our t. T is 2 to the power our lim size. So yeah, things have blown up in sophistication, basically. And so it was not at all clear from the offset that this would yield better performance results, but it did. a bit of a high-level overview of what we are going to want to do is we've just done a multiply or a square. So we've got a 13-bit number, a 13-limb number. And each of these limbs is going to be pretty filled up because we've just done a sum of cross products. Essentially, we want to remove as many, add or subtract multiples of our prime such that we remove all bits which are greater than or equal to a significance of 2 to the 384. So limbs 7 through 12 we're going to want to get rid of, and then the high bits of limbs 4, 5, and 6. Kind of, they straddle that dotted line. And so this is our game plan. We're going to want to subtract at some stage. So to avoid underflow, we're going to have to do something. We're going to want to get rid of limbs 7 through 12 with our first substitution. Let's carry limbs 4 and 5 up to 6 so that we can remove the high bits of limb 6 all in one go. That's going to be our second substitution. And then finally, we carry out all redundancy in our representation and profit. I got this lovely review comment telling me that I'd put a whole bunch of random constants in critical crypto code and not explain things. And I don't know why they said that. But here basically is a telescoping sum. So here's all these constants collapse to just a large multiple of our prime. We're going to add a large multiple of our prime. So whatever we do, whatever subtractions we do, we won't underflow. It's telescoping in that we're adding a copy of 2 to the 124 to one limb, and then subtracting a copy of 2 to the 68 from a higher limb. 68 plus 56 is 124, so we're adding and subtracting the same thing. Not only is this a large multiple, but each one of its limbs is sufficiently large so that we can subtract a limb from limb. And then we do our first substitution, a bit of modular arithmetic later, and we end up with the ability to substitute T7 in terms of T2, T1, and T0. And so this gives us a rule to eliminate limbs 7 through 12. To eliminate limb 7, again, vertical overlap of limbs means we're going to have to add. We add a shifted copy into limb 2, a shifted copy into limb 1. We subtract and add shifted copies into lim 0. And so this is what our code looks like. We're going to start with lim 12. Its reduction rule can be derived from lim 7 just by multiplying by 2 to the 5th. And surely enough, we add into lim 7, add into lim 6, subtract into lim 5, add into lim 5. As the formula would say, but to avoid overflow this time, we need to actually not only add into lim 7, but add a little bit of our lim 12 into lim 8. So yeah, lots of complications here, lots of caveats. And after our first substitution, we've just gotten rid of limbs 7 through 12. We've redistributed them into the lower end of our number by, in effect, subtracting a multiple of our modulus, which is lovely. What remains to be done is the high bits of limbs 4, 5, and 6 need to be substituted. So let's carry forward those high bits from limbs 4 and 5. Just some bit shifting, clearing, and adding. Everything's bit shifting with this. That's the lovely thing about Salinas methods. Everything's bit shifting. No proper multiplies. And then finally, we do one last substitution of all those high bits in lim 6. Notice that 4 and 5 are skinny now. And that's what our substitution looks like. Those bottom 3 blocks of code share the same format as the last substitution. We're bit shifting lim 6 to get the high bits, and then redistributing them, avoiding overflows. And then finally, we set our pre and post condition for each of our kernels to be that we've reduced and gotten rid of redundancy. That is, all of our limbs should be less than 2 to the 56. And so we just do a whole bunch of carries to accomplish that. We actually haven't fully reduced our numbers modulo p, but we don't need to. We just need the pre and post conditions of each of our kernels to be compatible, that is, to be able to compose. And we make everything skinny. That's what our carries do. And yeah, that's our algorithm from 30,000 feet. So the bit which will be relevant to a room of cyber people, I added 2,000 new lines of C into OpenSSL. And yeah, the code standards were kind of high. Like, they told me when I'd commented incorrectly. But there's this hilarious bit where they said, oh, I have a mate who knows maths. Let him get back to you. And then he never got back to me. So they just merged 2,000 lines of obfuscated maths, basically, from a new contributor. So yeah, it turns out if you wanted to, and I don't, this is a great way to backdoor most of the internet. Don't get any ideas. Yeah. So where to next? Again, I've set up these functions, multiply, square, reduce. They're upstream. They're ready to go in version 3.2 of OpenSSL. But there's further ASM optimizations that we can be doing on this curve, as well as powers a bi-endian architecture. It can run little endian or big, and there's some trivial patches to bring big endian support. I continue to provide community support for PowerPC, for OpenSSL and PowerPC, and I hope to touch on these curves and see if we can get some extra performance somewhere for anyone who's interested. That's my talk. Anyone got any questions?
Are there any questions in the audience? One over here.
Thanks for a great talk, Rohan. Before the Salinas method, the previous method that you compared against, could you give us a brief overview as to how it was running? And in particular, like, what sort of arithmetic operations did it use? Was it mostly shifts and adds as well, or was it doing some like multiplications and all this nonsense?
Yeah, good. Yeah, so essentially, the previous method is called Montgomery reduction. It has a nice Wikipedia page. In short, it's a ring homomorphism, again, on modular arithmetic. But it has this nice property where you can avoid doing any explicit divisions by a non-power of 2, basically. It's a anyway, so things become bit shifts again. Where we actually see performance gains, so here are some bonus slides. Basically, Salinas methods are hyper-optimized to the particular choice of prime. Montgomery's, however, is a generic approach. The real advantage, however, is that we can write code like this. So we can actually leave our carries to the very end. Conceivably, you could write this into Montgomery as well. But the primary advantage in leaving carries to the very end is that you already have an arithmetic-bound computation. And if you keep really, really loose dependency chains and you kind of front-load a lot of the arithmetic, then you open up your code to running really fast on a superscalar processor. So instruction-level parallelism is basically the answer, in short. Conceivably, you could, and the P256 code has an optimized Montgomery method. Conceivably, you could get similar optimizations out of that, but this seemed simpler, actually. But yeah, there's that. Yeah, thanks.